Hello, and thanks for joining us today. I'm Carrie Burton, your host for today's webinar. And with me today is Tim Presnick and Tim Batten to discuss using Renishaw's Virsa Raman Analyzer for remote sampling. Before we begin, please note that you are on mute and will remain in listen-only mode throughout the webinar. However, we encourage you to submit your questions or comments at any time during the session using the control panel on the right side. We will be answering as many questions as possible at the end of the presentation, and we are also recording today's webinar and we'll be sending the replay to you via email. And now I'd like to hand it over to Tim Presnick, U.S. Sales Manager at Renishaw Inc. in the Spectroscopy Products Division. Hey, Tim.
Hi, Carrie. Hopefully everyone can hear me okay. So let's go ahead and get started with the presentation. So really, this is going to be the story of a high-performance Raman spectrometer in a compact and portable unit. I have placed my, I'm going to get the laser pointer going. I have placed my LinkedIn and Twitter handles there, so I would appreciate if anyone who's listening today could take the time to connect with me, and if you have any questions, definitely ask during this webinar, but certainly reach out to me on one of those platforms and I'd be happy to connect with you that way as well. If you haven't ever, or if I haven't ever had the opportunity to speak to you before, then there's probably two common traits that I think I have when I'm giving these kind of presentations. One is I know that I am a scientific instrument maker. And to me, that means that what I'm trying to do is manufacture an instrument that is going to be able to answer your problems. So I measure my success based off of how well we do that, how well we help you solve your problems. I want to always introduce instrumentation that is going to give you the ability to gain new insight into your materials or whatever you're trying to research. And then on top of that, I'm going to measure my success again by seeing you publish for the first time that type of new insight. So that's something that I know about myself. And so a lot of my presentations are really focusing primarily on the hardware and the capabilities of that hardware, because I want to introduce that capability to you. And I want you to start getting your gears rolling in terms of thinking about how you're going to utilize that equipment. The other thing that I know about myself is that I really like Raman spectroscopy. I've been doing it for almost 30 years now. I've been looking at inelastically scattered light on tons of different types of materials. So I've been doing it for such a long time. I like it not only because I get to use lasers, and lasers are cool, but also I like the backstory. I like the history of Raman spectroscopy. And Raman himself, there is just so much history there that you tend to learn a lot about the instrumentation that he used, the experimental process, and I always feel like that makes me a better experimentalist in terms of trying to understand how these different components work. So that's kind of a long introduction, but that kind of gives you a sense of what you're in for. So in today's webinar, I'm going to focus primarily on a new instrument that we call the Virsa. The Virsa is a fiber-based portable compact Raman system. We're going to be talking a little bit about combining Raman spectroscopy with other analytical techniques. And then I'm also going to go into, hopefully, what you're going to find is a thorough discussion about the optimization of fiber optic probes for Raman spectroscopy. So I'm going to try to relay all this information in a compact way so that we can get through this together. Once I've gone through, or actually, before I really get into all of this information, I feel like it is important for me to lay a little bit of a foundation and talk about fundamentals of Raman spectroscopy and just general instrumentation design. And then once I'm done going through these points, then I'm going to get into talking a little bit about automating that type of remote sampling capability and the capability that Renishaw offers, both hardware and software. So, like I mentioned, I like the history of Raman spectroscopy. I was looking at this little booklet, which the ACS Historical Chemical Landmarks published. And what I read here was that basically Raman back in 1928 or so, when he was first really publishing his results, lasers didn't exist. So really at that point, he was using sunlight, and be able to concentrate that sunlight, he was using a 7-inch refractor telescope, which his institute in Calcutta was just recently procured. And I kind of like that idea too, that the telescope got 24-hour use, that Raman was using it during the day and the astronomers were using it during the evening. So probably they thought it was a decent investment. But using a 7-inch refractor, I can imagine that you're really taking a lot of that sunlight and you're concentrating it down. So Raman was really, he was looking for that subtle change in that energy of those photons. And so he would take a violet filter, take that sunlight, filter it away, and just make it a violet color. And then he would put a green filter in that same path before he would look at the sample. So the observer would be sitting over here. And if you have a violet filter and a green filter, you're not going to see any light coming through at all. But when you introduce a purified sample of some type, and he spent a lot of time purifying solutions to do this, then all of a sudden you can see a little bit of green light coming through. And that told him that there was a change in the energy of the photon, and that change in the energy has shifted or changed its color as well. And that is the basis of Raman spectroscopy. We're looking at that change in the energy of the photons. And so a lot of times what you'll be presented with when you're learning about Raman spectroscopy are these energy level diagrams where you're looking at ground electronic states and vibrational levels. And so in most cases, when we excite a sample with light, we don't see any change in energy. So that's called Rayleigh scattering. So when that light illuminates on the sample, no change in the color happens. But maybe 1 out of every 1,000,000 photons, when that photon comes down and hits the sample, it may give a little energy to that molecule. And so when it scatters off, it's coming off with a little bit less energy. The difference in the energy is really due to that vibrational frequency of that molecule. So when it scatters off, it changes its energy, and we're looking at that change in the color of that photon and trying to understand that. If the molecule itself is already in an excited state, then when the photon is incident upon that material, then what you'll see is that sometimes that molecule may impart some energy to those photons. And then in those cases, that photon will scatter off with slightly higher energy, and it'll be slightly blue shifted instead of red shifted. And so that's called anti-Stokes Raman spectroscopy. But it's less likely that those molecules will be in an excited state. And so we see very few photons that are actually anti-Stokes photons, and we focus primarily on Stokes photons. So that's the basic principle behind Raman spectroscopy. You need to excite your sample with a laser source or some sort of light source, and then you filter away the Rayleigh scattered light, and you look at the Raman scattered light, the light that has changed its energy. Also in that pamphlet, just as an aside really quick, I promise, we're going to be, what I found is that this is the first photograph of a Raman spectrum. And this is actually the dispersion of benzene. And so when he started to actually see these changes in photons, one of the first things he did was, as far as I can read, he went off and he bought himself an Adam Hilger spectroscope. And Adam Hilger was a company which is, I think, based in London, founded by Adam and Otto Hilger, 2 brothers from Germany. But those guys had actually passed in the turn of the century, and I think Frank Twyman was actually running the company at the time. And Frank Twyman built this Adam Hilger spectroscope using a Palmbroca prism, which is a linear or a constant deviation prism, which allowed you to see this spread of the light. Raman had one of these Adam Hilger spectroscopes, and the light was projected onto a photographic plate, and you can see that dispersion. As a light source, rather than the sun, he was using a mercury lamp. And in fact, he was using the G line, which is that 435 nanometer line, to illuminate the sample. And he was introducing a short pass filter, which meant that he was blocking this green light at 456 and 478 nanometers and allowing only the shorter wavelengths to come into the spectroscope. And then that sample, benzene, was illuminated by the light. And so what you're seeing in this top right photograph is that dispersion caused by the prism without any sample. And then you introduce the sample and you start to see these additional bands showing up. And I think what you're seeing is just multiple Raman features based off of the multiple excitation lines here. But I can clearly see that there's two bands here. And I'm just imagining this. I have no idea if this is true or not. But I think that first band is probably that ring stretching mode, that 992 peak. And then that second band is the CH stretch at 3060 or 3026, I believe it is. So this is probably the first time that you're really seeing the dispersion in a photographic plate. And it's not wholly different than what our CCD cameras see. So when I disperse light on a Renishaw spectrometer across a CCD, I'm not using a prism, I'm using a grating, and I'm breaking it up into its colors. But you can see the CCD camera is just acting like that photographic plate, but we can quantitate the intensity of the brightness of those photons and read out those intensities. So this is a spectrum of polyethylene I acquired just the other day. So it's all very interesting, and you can see maybe why I get a little bit passionate about Raman spectroscopy and the history here. But fundamentally, the instrument design here isn't significantly different than what Raman did. And so we always have a laser source, we illuminate some sort of sample, we look at the scattered light, we filter away the laser, and we only look at the photons that have changed in energy, and we disperse it onto our detector, which is a CCD. In the case of an Virsa Raman microscope, this is what the internal sort of guts of the instrument look like. We'll have a laser source, maybe some sort of bandpass filter. We'll deliver that light, conditioning it in some manner towards the Rayleigh filters, which reject the laser light and couple it into the microscope, where we're using objectives to be able to illuminate the sample. We're collecting all of that light back into the microscope through 180-degree backscatter collection. And then that light is presented towards the spectrometer where it's dispersed onto the CCD camera. So this is the fundamental design. And I feel like it was important for me to kind of go through and describe these components to you, because in a fiber optic probe, which I'll get into in about 10 or 20 slides here, a fiber optic probe is, it consists of all of these components. And so it's a good introduction, hopefully, to get us all on the same page. Now, there's a lot of different types of Raman spectrometers out there. And I think of the market in terms of Raman spectroscopy equipment as being broken up into 4 different tiers of instrumentation. And those can be handheld, portable, benchtop, routine lab type microscope-based systems, and then research-grade confocal Raman microscopes. The primary benefit and the primary use here, so definitely handheld, you get good portability, but it's primarily only really used for chemical ID. Whereas on the research-grade systems, you have the highest sensitivity, the best confocality, widest range of laser selection, and you can do pretty much anything with those tools. So there's definitely a good spread here. But what you don't have is this kind of capability in these lower tier instruments. The other aspect of this is that there are some similar components, but there's a lot of design differences, even at the research grade level. There's probably about 3 or 4 companies that make research grade Raman microscope systems, and we all do it differently. So it's kind of important to understand those slight differences in the instrument designs, because those can lead to slight performance enhancements for different types of samples. So you really want to kind of make yourself aware of what those differences are. Renishaw, in the world of Raman spectroscopy, or in the world of spectroscopy products division, which is where I live, all we do is make Raman instruments. We don't make any other type of scientific instrument. We make a variety of different types of tools, primarily the Virsa Raman microscope system. But more recently, what we've been doing is introducing instruments like the 802 or the 816, which are solution-based instruments. So they focus on solving one particular problem for that particular application area. And then we also do a lot of hybrid instruments where we're trying to combine Raman spectroscopy with other types of techniques like SEM, confocal laser scanning microscopes, and other tools like that. So all these instruments, definitely they offer the highest performance, but they're all lab-based instruments, and they're all microscope sampling tools. So that said, this is the reason why we wanted to develop the Virsa, is because we have a lot of customers out there who are trying to use our instruments and the performance that you can get on a research grade Raman microscope system on large samples or in environments where it's just not suitable to present those microscope or those type of samples to a microscope. So in this case, we have a simple turning mirror with an extension tube to look at large objects. We also have a steerable sampling arm, which can be used to motorize the position of an objective above a sample. We've also built large boxes with fiber optic probes in them, having video where you can position the laser delivery optics and the Raman collection optics right above your sample in very large samples that way using fibers. And then we've also done things like dual microscope stands and large gantries with video probes on them. So you can see that there's a lot of need for being able to look at big samples, but still retain the performance and the spectral resolution and everything else that you want on a research grade system. And that really was the motivation for building the Virsa. So this is a picture of what the unit looks like. It's behind me if you can see my video. This is a 19-inch rack mounted system. We have continuous laser power adjustment, and that laser power is defined as what the sample is actually seeing. It's using the same Renishaw Centris CCD camera that we put in our MVIA, which is a high sensitivity scientific grade system. And we can collect with that CCD camera 1,800 spectra per second, so it's fast. We have the ability to automatically switch between multiple laser sources. By default, the instrument, sorry, not by default, but as standard, we have 532 and 785 as options, but we have the ability of accommodating other laser sources as well. The box itself can support 2 lasers, and then we have an option for a separate box, which introduces a 3rd laser source as well. And then we can take those lasers and we can launch them into multiple fiber probes, and we can accept multiple return fibers from those remote analysis points as well. And then lastly, there's a triple grading turret using a Renishaw encoded grading stage on there as well. So we have the ability to vary the spectral resolution based off of whatever laser sources that we're changing there. The unit itself, it comes with the Virsa Analyzer, and then you use some sort of fiber optic probe, some sampling options. It's a simple USB connection to a laptop or PC, and then it's using the same wire software that we're using on our Renishaw and Virsa Raman microscope systems. So that's complete with all the data processing, data analysis tools that you can ever want, plus all the additional reporting functionality and everything. So there's quite a lot that we can do with this instrument based off of that kind of functionality. On the back end of it, you're going to see laser interlocks, trigger inputs, and then it's just standard 110 voltage if you're in the US market. But it's voltage sensing, so it'll adapt to anywhere between 90 and 240 volts. So it's a very simple system to integrate. In terms of performance, I have a couple slides here which really highlight the capability of this instrument, because that was our goal. We wanted to have portability, benchtop type system, but also have the ability to do things that the NVIDIA Raman system can do. So in terms of sensitivity, we measure the 4th order silicon peak, which is a pretty common option or pretty common test. In this case, I'm actually measuring close to 4:1 signal to noise based off of the peak to peak height in that noise area relative to the 4th order peak. Our spec is generally, we want a signal to noise better than 2:1. In terms of spectral resolution, our spec is full width half max on a neon peak of 2.5. In this case, I actually measured 2 wave number on the system behind me. We also have a linear dispersion, not linear, 1.5 wave number dispersion based off of whatever laser source that you're choosing there. So we can select the appropriate grading laser combination. So in terms of sensitivity and spectral resolution, we're definitely there. The big advantage, I think, is the resolution that you get spatially. You don't see this on fiber-based instruments. And so we have a lateral resolution which is less than 1 micron. And in this case, we went from doing a fast stream HR map where we collected, I think, about 500 spectra here pretty rapidly. Going from a metal surface to a silicon surface, and then simply plotting along the length of a horizontal profile of the intensity of the silicon band. So this black part of the spectrum is the intensity of silicon as we transition from metal to silicon. If you do a first derivative on that and you measure that full width half max, you're getting about 0.5 micron. So that's what your lateral resolution test would be. In terms of depth resolution, you simply sit on top of the silicon and you drill through the Z. In this case, we did plus or minus 5 microns at 200 nanometer steps in the Z axis. And then you plot the intensity of silicon as a function of Z. And in this case, we're shooting for less than 2 micron Z resolution with the ×100 optic, and I'm getting about 1.5 micron. So we're able to still retain that confocal capability with a fiber-based instrument and a portable Raman system. And this is just something that no other tool will do. So there's definitely some incredible enhancements to these type of instruments that you'll only see with the Virsa system. Now, in terms of how you might want to sample, we have obviously the Renishaw fiber optic probes. We have an option for having a video module with those probes and maybe an objective turret. And then you also have the option of being able to motorize the position of that whole assembly using this SP100. So I'm going to get into these quite a lot, and then I'm going to come back into the immersion and third-party probes a little bit later. But once you actually have this kind of capability, the motorized microscope objective turret, you now have a Raman imaging microscope system. So this is now a portable system with fiber probes that can still retain and have all the great capability of a standard optical Raman microscope system. So there's quite a lot of functionality with these type of tools. The Virsa probes themselves, amazingly, these turn on at 50 wave number, so you get close to the laser line performance. And then the total spectral range is really dependent on the laser and the detector limits, but generally the filters will perform to better than 4,000 wave numbers. And they are stackable. So if you have multiple probes, you can stack them, and that allows you to share excitation optics. So you can have completely automatic laser selection in the software without having to physically change anything on the instrument. And that I feel is really unique. Like I said, you can have the objective turret in here, and then on the box itself, we have a 5 megapixel video camera with white light microscopy on there. And that actually does a really, really good job at being able to visualize the sample. So I've had this 1951 US Air Force resolution target in my bag for 20 years. And it really looks like it. It's really dirty. It's got all sorts of laser burns on it. This bar here is group 7.6. This is the smallest feature on the bar. Those line widths are 2 microns wide, and I have approximately 25 pixels across that line width. So my pixel resolution with a 50x objective on the Virsa spectrometer is very, very good. I'm getting really high spatial resolution. I can visualize things very clearly. The white light illumination is perfect, I believe. And then your analytical spot size is going to be roughly about that half of that. So you're getting roughly about a 1 micron laser spot on top of there. So you can very easily position these probes on top of very small features and be able to acquire spectra confocally on top of those features as well. So that's one big advantage as well. We deliver 2 different types of probes. One is going to be intended primarily for bulk analysis. That's the VRP10 or Virsa Raman probe. And then we have another one which is intended primarily for confocal analysis, and that's the 20. And then again, you can still have the video option on these. You'll want to use the VRP20 when doing high confocal work. So if you're thinking about thin films and things like that, then that's a good application for it. Otherwise, the standard bulk probe will do really well on most measurements here. When we're coupling out to the stage, just really quick, this is the 3-axis positional stage. We have 75 millimeter of travel XYZ, and it's fitted with Renishaw Bionic 100 nanometer encoders here. So we get very high accurate positioning. We can still do our fast Raman imaging with this type of setup. And what I think is really unique is that you have free positioning of the probes themselves. You can either mount them vertically like they're shown here, or you can mount them horizontally. And what I like about that is that sometimes you have really big cryostats or maybe like an object on the wall and you want to analyze that. And so being able to just rotate that whole head and be able to do your Raman mapping in a vertical or in that horizontal position is something that I think is also really unique. You could turn it upside down. You could do whatever you like. So hopefully you've seen it, that you're getting this laboratory grade performance in a compact unit where you want it to be. So we think about all these different applications where we can take the system to the sample. It can be glove boxes, cryostats, deposition chambers, anywhere. But then we also think about combining Raman spectroscopy with other techniques, things like nano indenters or scanning probe microscopes or other types of applications here. So to touch on that just briefly, then what I have here is the combined techniques of being able to bring in the Virsa Raman spectrometer. I'm just curious whether or not you're actually seeing this view or not. So what I have here then is the ability to couple the Virsa Raman spectrometer to different types of instruments like the QFI thermal imaging system. So I have a couple images here, but I'm a little bit concerned that maybe you're not seeing it. I'm going to push forward and hopefully you are. Otherwise, so coupling to the QFI instrument and also maybe coupling into nanomechanical nanotribology instruments. There you go. I think you're seeing it now. So this is coupling the Virsa fiber probes over towards these type of tools here. You can see a Virsa probe with the QFI or Virsa probe with this Hysotron setup here as well. So it's very easy to couple in Raman spectroscopy with these instruments. In the case of the Hysotron, they have this nano indentation transducer, which is used to actually put these nano indenters in there. We shift the sample over to an optical view of the sample, and that's where we can do our Raman spectroscopy or Raman imaging and actually measure the amount of stress or strain in those materials using Raman. In the case of QFI, it's similar. We have a thermal imaging system, and then we can quantitate the temperature using Raman spectroscopy as well. And then we also have an option of being able to either just simply install the Renishaw control software on those third-party instruments, or we have the ability to have two completely separate PCs and using something called external controlled measurements, which gives us the ability to use JavaScript RPC to communicate between these two PCs when to collect data. And the advantage there is as we are collecting and controlling the Raman system with this third-party instrument, then we can also be shuttling that data into the Renishaw wire software, and that way it's really easy to correlate all that information. Speaking of correlate, which this is a function that we have now in every version of wire software. This is the ability to pull in images from other types of microscopes. So this could be an SEM in your lab or an FTIR or whatever it is. If you have some sort of view of your sample and you want to see that on the Renishaw system, you could use those images. You can load them into our software. We can align them to the optical view that the Raman system sees. And then you can use that SEM image or whatever it might be to actually drive the motorized stage and navigate on your sample and define areas where you want to do your Raman data collection. So it used to be that I was always saying, if you can see the sample, I can focus a laser beam on top of it and I can get a Raman spectrum of it. But now you don't even need to see the sample with an optical technique. You can use different techniques like an AFM or electron microscope, and you can use those images to be able to define areas where you want to collect Raman spectroscopy. So this is a really interesting functionality that's available freely within all versions of our wire software. Sorry, not all versions, the latest version of our wire software. That allows us to be able to take those third-party images and bring them into our instrument and use that. So That said, let's get into the basics of fiber optics and fiber optic probe design. We have a lot of different types of fiber probes available in the market. There's a lot of different companies making fiber optic instruments. And when you're thinking about maybe applying Raman spectroscopy using fiber optic probes, then it's important to understand the benefits of each of these types of probes and try to figure out which one is going to be best for your particular application. So the questions that you might be asking yourself are, what laser wavelengths do these fiber probes support? What fiber diameters are they using, and what's the length of that fiber optic cable? Because maybe your experiments are going to be placed far away from wherever your spectrometer will be. How are the fibers terminated? Because you're going to want to be able to simply adapt those fiber probes to your spectrometer. And then you start to think about things like the filter cut-on. If you're looking for a peak at 100 wave numbers, are these probes going to allow you to see that? Or do they cut on at 200 wave numbers or 300 wave numbers and they mask that signature? Also, what is the spectral range and what are the transmission properties? Because sometimes the filters that are used in these probes have pretty high ripple in them, and that ripple ends up being something that complicates the spectral results that you acquire. So you want to try to understand those kind of characteristics. Also, what is the analytical volume and the working distance? And then what kind of conditions are my probe going to be working in? Is it going to be a high temperature or low temperature? I remember doing an experiment for a customer where we were measuring liquid hydrogen at 20 Kelvin using fiber optic probes. And so those kind of extreme conditions need to be understood so that you can have a probe which is designed to do those kind of settings. And then lastly, among this list here, what kind of fittings do you need? If you're adapting this in some sort of process application, are you threading it onto a pipe? What kind of adapters do you have there? And so these companies have gained a lot of success in terms of what their business is based off of designing to solve these kind of problems for all sorts of different customers. And they make all sorts of different types of probes. Any of these probes can be coupled to the Renishaw Virsa spectrometer. So when you come to me and you ask the question or you tell me directly that you want to use fiber optic probes, I'm going to want to know a little bit more about that experiment. So I'm going to want to know what kind of sample are you measuring and what are you trying to measure about that sample? What laser source is best for that sample? And there I can help you because a lot of times I've seen a lot of applications out there and I understand which laser sources may be beneficial, but I have at my disposal the ability to do quite a lot of literature research and figure out what laser may be beneficial for that type of sample. And then where is the sample going to be located? Is it going to be in a deposition chamber? Is it going to be exposed to air, or is it going to be within a glove box? How are we going to do this analysis? Basically, what I'm trying to figure out is how does this probe need to be configured to be able to do the measurement in the most efficient and reliable manner. The things that I'm thinking about in the background are really related to the probe design. And so to get back to how these spectrometers are built, when we're thinking about microscope systems and how we are introducing that laser beam to our samples, we think a lot about the delivery of the laser light and how the objectives behave and how they interact with that sample. So when I take a laser beam, and most lasers that we couple in, they're going to be about a 1 millimeter or even smaller beam diameter. If I just take that 1 millimeter beam diameter and I couple it to a microscope objective, I'm going to be underfilling that lens. The back of your microscope objective has an entrance pupil, and that entrance pupil is going to be maybe 3, 4, maybe up to 10 millimeters wide. So if you took a 1 millimeter size laser beam, you're going to be underfilling that lens. And the net effect is that you're going to end up not getting the full numerical aperture of that optic, the full curvature of that lens to concentrate all that energy into a nice small spot. And we know that laser spot size in a microscope-based system is based off of not only the mode quality of your laser, that m² value, but the 1.22 times the wavelength divided by the NA. And so if you are not using the full numerical aperture of the objective to concentrate all that laser beam into a small spot, then you're not going to end up with a tight volume. You're going to end up with a bigger laser spot and a larger depth of focus. So we spend a lot of time in our Raman microscope systems to make sure that we properly fill the aperture. We don't want to overfill the optic and throw photons away, and we don't want to lose numerical aperture benefits by underfilling the optic as well. And all of those go to defining lateral and axial resolution as well. So really, numerical aperture with microscope objectives is important. And that's true of a lot of applications here. So getting into fiber optics, I snapped these pictures yesterday, actually this one this morning. This is a basic fiber optic patch cable that we have, and this cable itself, if you look at the FC termination here, this is what the fiber looks like. The fibers themselves, you'll have a core, and that core in this image is a 50 micron core with 125 millimeter cladding around it. The core diameter is something that's important to understand when you're using fiber optics and developing fiber optic probes. And I'll get into the reason why that is important in a second here. The other important thing to understand is the numerical aperture of your fiber optic. Now, fibers, they work based off of having the core diameter having a slightly higher index of refraction than the cladding. And so when that light introduces, or you shine light into a fiber at a particular acceptance angle, you're going to get total internal reflection based off of that change in the index of refraction. And when that light exits out of the fiber, it's going to exit out in a cone. And that cone is the numerical aperture of the optic. And you can figure out what that cone diameter is, what this acceptance angle is, by looking at the simple equation. So the NA or N numerical aperture is just sine theta, which is equal to the square root of the square of the cores, or the difference between the square of the cores. The other thing that I worry about sometimes is where am I going to place a lens? So if this is an actual lens here, I want the focal length of that lens, the diameter of that lens, to be able to equal that that numerical aperture of the optic. So I can collect all of that light and collimate it out. And the focal length here may be dependent on what my beam diameter is going to be as well. So these are things that I start to think about a little bit. So when I take those fibers, and I'm going to have a laser delivery fiber and a Raman out fiber. So this is going back towards my spectrometer. When I take these fiber optics, the first thing I'm going to do is I'm going to collimate the light coming out with some sort of lens and put it into this infinity space where I can introduce some filters. Now, the first thing you want in a fiber optic probe is a laser bandpass filter, pretty similar to what we have in our Raman spectrometer when we're coupling this to a microscope. The use here is actually when you put a laser beam into a fiber optic, on the output of that fiber optic, you're going to get the laser coming out of it, but you're also going to get the Raman spectrum of the fiber. So it's important to be able to put a bandpass filter in there so that you're only seeing the laser beam illuminating your sample and not seeing the Raman spectrum of the fiber optic, which would complicate your results. So we'll use a mirror to deliver light towards a Rayleigh line rejection filter, which again delivers the laser beam to the sample. And then you start to worry about spot size on your materials. So depending on exactly what your experiment is, you may want a small laser spot, or you may want a big laser spot. You may want a larger depth of focus, or you may want a tight depth of focus. So when I'm thinking about these things, I'm thinking about what is that core diameter, because I'm going to end up projecting the image of the core diameter onto my sample. So your spot size is no longer necessarily governed by the numerical aperture of your lenses, but it's more governed by the ratio of those focal lengths times the core diameter, so that if I have a 1-to-1 ratio in terms of these focal lengths, I'll end up getting a 50 micron laser spot on the sample. And then oftentimes what you'll see is that on the collection fiber, you get it a little bit bigger than your excitation fiber, so that you're assured to be able to collect the full excitation volume coming back into the instrument. So that's generally how fiber optic probes are designed. And this is pretty common. This is you're going to see this in all sorts of different types of fibers or fiber optic probes. You'll see different arrangements, different types of filters, different types of fiber optics being used, but fundamentally this is what's happening inside of every single fiber optic probe. This focusing optic, the choice of that focusing optic is really going to be dependent on the materials that you're thinking about. So the ball lens, which is a pretty popular lens right now in these touch probes, especially by Metrics, then this ball lens is used for immersion and touch probe type applications, and it makes it really easy to be able to sample liquids and just simply touch the probe up against a solid material and get a spectrum of that material. So that's great for just bulk applications. If you were trying to do something inside a deposition chamber or at high temperatures, then maybe that's not necessarily what you want. Maybe you need some long working distance so you can stare through windows and be able to get down to wherever your experiment is taking place. So those long working distance optics generally have lower numerical aperture lenses, and these can still be microscope objective lenses. But then you're still concerned about your analytical spot size. So the effective focal length of a microscope objective is simply the tube length of the microscope divided by the magnification. So if this high NA optic is a 50x objective and it's a Leica 50x objective, then this would have an effective focal length of 4 millimeters. It's different than the working distance of the optic, but you can then use that effective focal length, understanding what lens is collimating the light out of your fiber, to get a sense of how big your laser illumination is going to be. So this gives you the ability to choose which optics are going to be best for your particular application, whether it's thin film or bulk analysis. The last thing I'll say about this slide really is that when you're choosing these long working distance optics with lower NAs, there's sometimes a benefit there because that lower NA is going to give you a larger depth of focus, and that gives you, it makes it a little bit more forgiving for quality of focus on the sample, especially if you're doing handheld fiber probe analysis. Then you want to have some sort of depth of focus there so that the quality of focus isn't necessarily affecting the quality of the Raman data. So if you have a lot of surface variation, then a lower NA optic may have some benefit to you. So that's brief introduction to fiber optic probes. Hopefully you found that interesting. What I'm going to talk to you about next is some of the software and hardware capability that we have with the Virsa system. And I'm going to begin that with something called CAP. So if you have ever used a Renishaw system, you may have seen within the Renishaw file program group a program called CAP that has a little beanie with a propeller on it as the icon. I sometimes think the software guys have too much fun developing our icons, but this is the CAP software. CAP stands for Custom Analysis Package, and this is a package which allows you to automatically collect your data, so you can now define your measurement, what's gonna happen. You can have that with motorized positioning, so you can collect multiple data points, and as it collects the data, then it's going to analyze the data by either background subtraction and curve fitting and other things like that. It's also going to give you the ability to then take those results, those curve fit results, and then perform some math on those. So if you wanted to understand the relative ratios of a 2D versus G band, then that's something that is really, that the CAP is designed to do that. And it will do that automatically. So then it will process all the data and just report that final ratio number, which is really what you're after. And then when it reports that number, it'll tabulate it or just put the result out to your LIMS system. Really simple to set up. It's meant really primarily for these process type applications and a QA/QC application, but I can really see the benefit if it's just a routine analysis to be able to use CAP in an easy way to process and deliver answers quickly. So in the case of using it with a Virsa Raman spectrometer, then it's something that we can use pretty easily here in a remote analysis technique. We also have options for triggering, and triggering can be useful for detecting or being able to synchronize data acquisition with different events. And there's two different ways of doing triggers with the Renishaw system, either through software or through hardware. And I'm just going to briefly describe both. Software triggers are designed really with sort of start-stop functionality. It is just monitoring the Windows event log, so it really just gives the users the ability to simply program independent of the Renishaw system completely. The ability to program some way to synchronize and initiate or end experiments using the Renishaw system. We provide sample code. If you have a Renishaw Wire DVD, you have the sample code. because it's on that DVD that came with your instrument. So that we provide that sample code, and there's also a sample program there to demonstrate that functionality. So it's really simple to use. It just simply initiates your experiments based off of whenever you tell those experiments to start. Hardware triggers can actually be used to capture very rare or complex events. And we can initiate and respond to hardware triggers based off of different instances in the data readout. So I'm just going to briefly describe an experiment where this was used successfully recently. And this is really looking at the para-nitrothiophonol. This is a sphere segmented void gold SIR substrate where that substrate had been submerged in a 50 millimolar solution of that NTP. And that allowed a monolayer of the NTP to exist. Now, all this work was done at University of Southampton. So this is a specially designed cell that they have where that SSV substrate was used as the working electrode. And then you have simply taps there. But we're going to look through this window down on that electrode surface and perform these CV experiments. To be able to integrate on the triggering, there was used a Metro Model Lab with the AutoLab Nova software, and that gave us the ability to be able to initiate triggers at different points along a CV gram. So when we're doing these experiments, the first cycle that you go through, you see this very large reduction in the NTP, but the subsequent scans don't show that reduction anymore. So it's generally thought that you're changing from the nitrathiol to an aminothiophenol. And so we're starting to see those kind of applications there. So with the hardware triggering, we were going to be driving from 0 volt down to minus 1.2 volt and wanted to collect spectra at 0.1 volt increments along that CV gram. So in each of these cases, we would hold for 100 seconds and then initiate a low power 1 milliwatt 785 measurement for 10 seconds and acquire the Raman spectral data. And as we're starting to do that, then we're starting to see the NTP bands, the cyano band kind of disappearing and starting to see some of these additional bands reappear. So we're watching that reduction occur all fully automatic using the hardware triggering. So this is simply just the plot of the intensity of that one band and seeing that decrease over time. So that's just a simple hardware application there. Hopefully this wasn't too confusing to you. But today, what did you learn? Well, you learned that you want to buy a Virsa Raman Analyser system because it's the best Raman system that you've ever seen. But you've also learned that it is very easy to combine these Raman instruments with different types of techniques, and that the Renishaw software and hardware has a lot of capability that makes it very easy to integrate with other experiments. So with that said, like I mentioned, hopefully you have some questions for us here, and there have been questions coming in. Connect with me on LinkedIn and on Twitter, and certainly visit our websites. And at this point, I'm going to ask Tim Batten to join me. And
yes, I will. We did get some questions in.
Excellent.
So Tim Batten, if you'd like to say hi and introduce yourself.
Hello, everyone.
Oh. All right, so one of the first questions that we got, I think, is a two-part question. They ask if you can add the XYZ stage to the same system, and if so, do you just switch it through the software, or do you have to do some hardware changes?
Okay, well, so the XYZ stack is independent of the probes, so you can add it to the system later, or you can purchase it with the system. You can use it in conjunction with a single probe or a probe with a video unit. Now, if you have multiple probes of different wavelengths, they can share the same video unit and the same stage stack to do mapping. And this is just done in the software. So you basically, in our wire software, if you want to choose different laser wavelengths, you just select laser from the drop-down list. There's no sort of manual alignment or configuration. You don't need to change any of the hardware. That's it. So it's very straightforward and simple in that respect.
Perfect. And then they ask, regarding coupling, what is your view on the efficiency by direct coupling and single mode fiber optic? Both can be very similar with respect of loss, or are there any benefits over one to another?
Definitely more tedious. Single mode fiber optics being on the order of about 8 to 10 microns possibly. Then it becomes more difficult to be able to couple the laser into that fiber optic, especially if you're doing it with high power lasers. A slight misalignment may actually burn the cladding, and that may burn your fibers as well. And definitely that would cause you to have to repolish your fibers. And then it's also more difficult to maintain that alignment. A lot of your Raman systems and the fiber probes themselves should be designed so that all of that is hardened inside the probe. So you don't necessarily need to worry about the alignments themselves. But if you're doing this on a bench and you're trying to launch a laser into a fiber probe, there's a lot of degrees of freedom, a lot of possibility for things to make it more difficult to couple into those. Yes, using single mode fiber optics they have some benefits, producing small laser spot sizes, and you have the ability to potentially, because they're also single mode just means that you're using a single transverse mode of light there, and you're getting a single polarization from those probes as well. So there's some advantages to using those, but in fiber probe applications, they're not typical.
Got it, perfect. All right, so we do have a few more questions. However, I'll say to the attendees, if you have any more questions, please go to the panel on the right side and ask some questions to us, and we'll get to them if we can. So the next question would be, how easy is the system to set up, and do you need to do laser alignment?
Yeah, it's actually all easily coupled in. So there is no setup. It's just the box behind itself. The fibers that we're using on our probes are simply FC connected. FC connectors seem to be pretty much a standard for using fiber probes. So it's very easy to simply couple those other probes right into the instrument. So there is no setup really. It's just a box that you pull out and you couple your fibers and you're done.
Yeah, so just to follow up on that point, so we're also using this system as a transportable system, taking it to different sites. So one of the applications is art heritage. So you take it to a museum, move it around the galleries, things like that. And it normally takes longer to get out of the box than it does to actually set it all up and connect. So basically, you're connecting in 2 or 3 adapters, a power lead, a USB cable, and then it's just start and go.
Perfect, I think I could do it. And then next question, why do we need good laser power control?
All right, so definitely you know, Raman being a non-contact, non-destructive technique, only in the case where you didn't burn your sample with too much laser power. And what we're trying to do is we're trying to concentrate all that volume, all that laser into a very tight volume, and that leads to very high laser power density. And that high laser power density can cause heating on your material. That may change the molecular structure, and that can also burn your materials. And so you want to have very fine control over how much laser power is illuminating your sample so that you can avoid those kind of damages. Do you want to add to that at all, Tim?
Yeah, so I mean, the laser power you use is directly proportional to the measurement time. So if you can use twice as much power, you can halve the measurement time. However, in this circumstance where you damage your samples, obviously that's the end of it, but you don't want to be in a situation where you're using 1/10 of the laser power you could use, because it's going to make your measurement times very long. So you want to be able to edge the laser power up towards the threshold for any sort of induced damage on the sample, so you're basically running the measurements as quickly as you can. And that's also really vital if you want to start doing fast mapping and things like that, where you're taking lots of measurement points.
All right, next question is, can one use a fiber probe without a lens, moving it to an intimate contact with a surface under study in a liquid environment?
Yeah, you could. So I think this is sort of the principle of a fat probe from Kaiser. You don't really have a collimation, or sorry, focusing there. You're just looking at a very large volume. I think in those cases, you definitely want to boost the energy, maybe use a very high laser power, because you're not going to have the benefit of having high NA optics collecting the light, and you're also not going to have the benefit of being able to focus the laser beam to a tight spot and see high energy density. Both of those are going to affect your Raman signal intensity. So yes, absolutely, you don't need a focusing optic on there, but it will reduce the efficiency of making your measurement. So you'll need to compensate either by doing longer exposure times, or you'll need to boost your energy quite a lot to be able to see some Raman signal.
Yeah, so to follow up, so we do provide also touch type probes. So if you do have samples where you're not unhappy to touch the sample, you can literally get a surface measurement directly. So things like maybe if you're measuring coatings on parts where you basically can't access the part readily, you then have a probe, you just touch onto the area, get a big volume collection, and it gives you the Raman spectra over that area.
Okay, next question is for CV Raman measurements, can you also do Raman imaging?
Yeah,
Sorry.
it's for those cycle voltammogram measurements with Raman spectroscopy. Can you do Raman imaging? And the answer is absolutely yes. It's going to take a little bit longer than just a 10-second measurement. So depending on what your point density is, what size area that you want to acquire, what kind of Raman signal intensity you get from a single point, that will define what your Raman imaging experiment is. But yes, absolutely, you can do Raman imaging on the surface of the electrode at different points along the scan. And then we could actually stack those images as well and be able to do some nice little animations to show you how those images are changing.
All right, we have 2 more questions, and I see we're getting tight on time, so I'm going to ask them, but just keep in mind, you might want to keep your answer short. How much minimum power variation is possible when you have mentioned recently that we can vary power continuously?
Mm-hmm.
And they also said, thanks so much for the nice presentation and explanation. So I'm sure everyone feels they're experts now.
So the laser power variation, I believe we stated as 0.1 milliwatt increments of laser power on the sample, and it'll go from 100% power down to 0% power. So that kind of gives you the sense of what you can do there.
Perfect. And the last question we have is, are cover slips not recommended, or are they okay to use with Renishaw's instruments for biological tissue specimens?
It's not that they're not recommended. It's I suppose if you're placing a sample underneath a cover slip, you're probably trying to keep it in the environment that sample exists in. So maybe you want to keep it wet and healthy in that manner. So there are specific cells that you can have where I'm thinking things like Oco Labs makes an incubator cell, which makes it really easy to be able to keep cells happy and alive. If you're looking at tissue and you're keeping it under a cover slip, that's not a problem at all. This is where the benefit of doing confocal measurements using fiber probes really has some benefit, because in certain cases, the cover slip can add to the spectral result in a bad way. So certain cover slips may have a strong fluorescence to them. And if that's the case, then doing a highly confocal Raman measurement will minimize the contribution of that fluorescent light and allow you to see the spectral signatures of your tissue below that.
Okay, just something to add there. If you do want to do measurements with cover slips, absolutely fine. You get better performance if you use cover slip corrected objective lenses though, and that's quite important because that basically gives you that improvement in performance that you would otherwise lose out on. As Tim mentioned, cover slips can be of varying quality depending on how much you pay, and you will see that in the Raman spectra. So one option is also not to use glass cover slips, but to use calcium fluoride cover slips or quartz cover slips, because they give lower background if you need to use them.
Yeah.
Awesome. Well, thank you so much, and thank you everyone for the great questions. And thanks again for joining us today. We hope to see you again at our next webinar, where Tim Batten will be discussing combining Raman spectroscopy for richer science. So keep a lookout for an email with the information on that, and follow us on social media. And if you have any questions or additional questions, please contact us via email at usa@renishaw.com. Thanks so much and have a great day.
Thanks.